The science of two-way slab reinforcement. Welcome. Today, we are breaking down the reinforcement logic of the two-way slab. We define a two-way slab by its span ratio. When the longer span, Ly, divided by the shorter span, Lx, is less than 2, the slab is designed to carry loads in two directions. Unlike a one-way slab, where the load travels primarily to two parallel beams, a two-way slab distributes its weight to all four supporting edges. This creates a dish-like deflection, meaning we must reinforce both the x and y axes to handle the resulting tension. A common point of confusion is the difference between main and distribution bars. In a one-way slab, you have main bars in one direction and temperature steel in the other. In a two-way slab, we have main reinforcement in both directions. Shorter span Lx, this direction usually carries more load. Therefore, the main bars for the shorter span are placed in the bottom-most layer to maximize their effective depth. Longer span Ly, the main bars for the longer span are placed directly on top of the shorter span bars. Spacing rules. According to codes like ACI 318 or IS 456, the maximum spacing for these bars is typically 3 times the slab thickness or 300 millimeters, whichever is less. We don't just throw a uniform grid of steel across the whole floor. We divide the slab into strips. Column strips. These are the regions directly over or between columns. Because the stiffness is higher here, the bending moments are greater. We pack more reinforcement into these strips. Middle strips. These are the center areas of the slab. In a continuous slab, we also have to deal with negative moments at the supports. This is why you see steel at the top of the slab, near the beams or columns, and steel at the bottom of the slab in the center of the room. One of the most unique features of two-way slab detailing is torsional reinforcement. When a slab is loaded, the center goes down, but the corners want to lift up. This curling creates diagonal tension that can cause cracks at a 45 circ angle. To prevent this, codes require a specific mesh of steel at any corner where the slab is restrained by beams or walls. This mesh consists of 4 layers of steel, top and bottom in both directions. It usually extends a distance of 1/5 of the shorter span from the corner. If you skip this, your slab will likely develop structural cracks at the corners over time. Punching shear and special systems. In flat slabs, which are two-way slabs without beams, we face a danger called punching shear. This is where the column could punch through the slab, like a nail through cardboard. To reinforce against this, we use drop panels, thickening the slab around the column. Distribute steel into column and middle strips. Never forget your torsional reinforcement at the corners. Ensure a minimum concrete cover, usually 20 mm to 25 mm, to protect your steel from corrosion. The engineering of two-way slabs. In structural engineering, the slab is the primary horizontal element that captures and transfers live and dead loads. While a one-way slab acts like a bridge between two supports, a two-way slab is a more complex system that distributes weight in two perpendicular directions simultaneously. The primary way to identify a two-way slab is through its geometry. We look at the aspect ratio of the spans. If the ratio of the longer span Ly to the shorter span Lx is less than 2, the slab is classified as a two-way system. This usually occurs in square or near square floor plans, where all 4 edges are supported by beams or walls. Load distribution and behavior. The load is distributed to all 4 supporting beams. Because the slab is resisting bending in 2 directions, it is inherently stiffer than a one-way slab of the same thickness. This allows engineers to design thinner slabs for larger areas. Common structural variations. Two-way slabs are not a one-size-fits-all solution. They generally fall into 3 categories based on the architectural requirements. Slab on beams. This is the most rigid version, where the slab rests on beams on all 4 sides. It is ideal for heavy industrial loads or structures where high stiffness is required. Flat slabs. These slabs transition directly into columns without the use of beams. This creates a flush, flat ceiling which is perfect for running mechanical ducts and plumbing. However, these require drop panels or column capitals to prevent punching shear failure where the column literally punches through the concrete. Waffle slabs, for very large spans. A solid concrete slab becomes too heavy. A waffle slab uses a grid of ribs on the underside, removing unnecessary concrete and creating a lightweight, high-strength egg crate structure. The reinforcement grid. Because the slab experiences tension in two directions, the reinforcement strategy changes significantly compared to one-way systems. In a two-way slab, we place main tension reinforcement in both the X and Y directions, creating a dense mesh. This mesh must be carefully positioned to handle positive moments at the center of the span bottom steel and negative moments over the supports top steel. One critical detail is torsional reinforcement. In a two-way slab supported by beams, the corners have a tendency to lift or curl upward under load. To prevent diagonal cracking at these corners, engineers specify additional U-bars or mesh reinforcement at the exterior corners to tie the slab down and resist torsion. Summary of benefits. Why do engineers choose two-way slabs? Versatility. They are the best choice for square or rectangular bays. Our large-scale projects. Understanding the two-way slab is essential for anyone involved in modern high-rise construction, as it provides the perfect balance of strength, aesthetics, and material efficiency.